everyone, welcome back. We're now going to continue our work in section 14.4, thinking about gradients and directional derivatives, by looking at part B of our preliminary example. So in this part B, we're going to start getting into the directional derivative, and we'll see why the gradient is helpful in computing it in the end. But first, let's just look at what the question is asking us. So part B says, approximately how fast does the temperature change at the point P, which is 1, 1, as you move towards the point Q, which is 1.66 and a half. We're going to see the diagram below, and we want to include units in your answer. So let's just unpack exactly what they're asking. So we're starting at point P, and we have some temperature, and we want to know the rate of change of that temperature as we move to Q. So we're not just asking what is the change of the temperature, which is what we did in the previous section. We want to know what is the rate of change of that temperature as we move to Q. So we have seen something similar in our multivariable calculus class, where we're looking at how does our output, or in this context, temperature, change as we move in the direction of Y or X, but not as we move in the direction of a specific point. So that's what we're going to calculate. Well, to do that, what we can do is just calculate the change of temperature compared to the change of placement. So let's write that out. So the rate of change of T is just going to be the change of T over, in some sense, the change of the inputs. And what we're going to do for that change of inputs is to compute the distance between P and Q. So let's go ahead and compute that out. So our change in temperature, so if we're looking at point P, we can compute the temperature here, and I'll just do it up to the side. Feel free to pause the video and do this on your own. So T of 1, 1 is just going to be 1 minus 1/4 1 squared minus 1/4 1 squared. And then T of Q, our Q here is 1.66.5. We just plug that into our function as well. So go ahead and work that out on your calculator. For P, we should be getting 0.5. And for Q, we should be getting 0.25. And notice we can also just check that on our level curve. Maybe some of you saw that. So we have P and Q labeled here. So at P, we are at 0.5, and at Q, we are at 0.25. Okay, so what we want to do is take the difference of those two temperatures. So meaning T of Q minus T of P. Then again, we're going to compute then the distance from P to Q, or the length of the vector PQ. So that's going to be 0.25 minus 0.5. And then to compute the distance between two values, or between 2 points, we're just going to use the distance formula. So that would be the square root of the difference between our x values, so 1.66 minus 1 squared, plus the square of the difference between our y values, so 0.5 minus 1 squared. So now you can get out your calculator and compute what this should be. And you can check me here. I'm getting around negative 0.30. And so what should the units be? Well, our numerator units are in degrees Celsius. The denominator is a difference of locations, which we were told x and y are measured in centimeters. So when we subtract centimeters, we still get centimeters. Finding the different distance between 2 points would just, again, give us centimeters. So the units being degrees Celsius per centimeter. So this number here should tell us how much our temperature changes per centimeter as we move from P to Q. So one more thing about this number, what we actually computed here is an estimate, an approximation of the directional derivative of T at the point 1, 1. So I'm going to write that out just so we have it. So this number here is an estimate of the directional derivative that in quotes because that's our new concept of this chapter. Directional derivative of T at the point 1, 1, but specifically in the direction of the vector PQ. So there's a lot of components here, notice. So we're looking at the directional derivative, sure, but it's at a point in a direction. So how can we make sense of this directional derivative or this value on our curve? Well, let's take a look at our graph. So the question we're asking here is how the temperature changes as we move from P to Q. So if we move from P to Q on the XY plane or along the plate, the temperature is moving from this point here, this temperature, to this temperature. So if we draw kind of that line here, what we just computed is the slope of this line. But again, that was just an estimate. If we wanted to find exactly how that temperature changed, we would need to compute the tangent line at the point P in the direction of Q. I'm going to draw that in here. And we would need to find the slope of that tangent line. So again, we compute an estimate, but to find the exact value, we need to find the slope of the tangent line. And more specifically, what tangent line are we referring to? Well, the tangent line of our surface at P, but in the direction of PQ. So as if I were to kind of project this PQ up and had our tangent line in that direction. So notice our line is not just the line that goes between the 2 points above P and Q. That is the estimate that we found. But to actually know how that temperature changes, we need to follow the slope of the tangent line at P in the direction of Q. So I'm going to write that down here at the bottom of our work here. So note, this is a note on how to find the exact directional derivative. The exact value of the directional derivative would be the value, or rather the slope, would be the slope of the line L above. So let me label that line. We'll label this line L. So we need to compute the slope of L, the tangent line at P in the direction of Q. Tangent line at P in direction of Q. So now we're no longer looking at the direction being just X or Y, but being in a particular different direction, in the direction PQ. So it turns out there's a really nice formula for actually computing the slope of this line that we just described, and that is computing that directional derivative. So let's move here to the next page and look at that theorem that gives us that super slick way of computing the directional derivative. So to begin, let U vector be a vector that's a unit vector in particular. So that means it just has a length of 1. Length 1. Clear that 1 up a little 1. If f is a differentiable function, then the directional derivative, denoted f sub u, which is the directional derivative in the direction u, can be calculated as follows. F sub u at AB is equal to the rate of change of F at AB in the direction of u. So we saw that in the previous example, but it can be computed the following way. Computing the derivative and the partial derivative with respect to x at AB times u1 plus the directional derivative with respect to y at AB times u2. So one really cool thing that we can notice here is that we see the components of the gradient coming in here, and we see those components of u. And really what we're doing here in this formula is just computing a dot product, where we're dotting the gradient of f at AB with the vector u. So a couple notes here. First, one caution before just using this formula willy-nilly. This u vector must be a unit vector. So that is something very important to keep in mind. And then if you want to know more details about how this directional derivative actually comes to be, why it is, in fact, the slope of that line that I described, then there is a more detailed derivation of it. I'm going to save you all the details in the video, but I encourage you to look at the solutions, our note solutions, and check it out for yourself. You can also probably YouTube or Google derivations of directional derivative for some other helpful geometric pictures. All right, thanks for watching.